organized the Terra lecture series with the GSI geologists, and it was a 5-lecture series. And after the lockdown period, I think this is the first offline Terra lecture. So again, I would like to welcome our guest, and I would like to request our head, Dr. Praveen, to introduce today's speaker. Thank you. Like to welcome our guest and
a very good afternoon. It gives me great privilege to introduce the speaker, Dr. Jahnavi Punekar, who is an alumni of the department. I'll begin by saying that Dr. Jahnavi was here way back before we became autonomous. And the reason I'm saying is she graduated from St. Xavier's College in 2004-2007 with the first rank in geology. Not only that, it's still a record that she was 7th rank in the university amongst all graduate students from Mumbai University. That record has not yet been broken, and I don't think it will ever be broken because we became autonomous. She is also the recipient of the Noshirwan Setna Scholarship for the highest marks in geology in BSc 2, the Dayanand Yellow Scholarship for securing highest marks in geology in BSc 3. Now, unfortunately, these are not available to our students because, again, we have become autonomous. So, you'll have lost on that too. Well, then, from here, she proceeded to the IIT, where in her jam, she secured the 5th rank in jam. After joining IIT, she gave a gate and again stood first. She then went on to move to greener pastures, I would say. That is, she went to Princeton, where she worked on the Cretaceous Paleogene boundary mass extinction in planktic foraminifera. She has held various positions. Earlier to that, she worked on the benthic foraminifera as a paleomonsoonal indicator in the Arabian Sea, as a summer intern in the National Institute of Oceanography. That also happens to be my lab, if I'm not mistaken, Jahnavi, the micropaleontology lab. She's also worked on foraminifera taphonomy and pH effects in IIT Pune, and now she's a professor in IIT Mumbai. IIT Bombay, Mumbai. Let me be very correct on that. Well, she has a lot of publications. I will not take much time from what I can see here. She's also delivered a lot of presentations at conferences. She has a lot of interests. Her interests are basically in planktonic foraminiferal micropaleontology and biostratigraphy. Foraminifera as environmental proxies, mass extinction and faunal turnover events in Earth history, geochemical proxies for paleo environmental reconstruction, and a lot more. She also happens to get a lot of funding, and getting funding is not easy. She is a DST Inspire Faculty Award. She's got funding from there. She's got also the DST SERB Extramural Grant. She is also a recipient of the Canadian Geology Fund Fellowship from Princeton, a recipient of the DST Inspire Faculty Award. Something else that is interesting, she featured on a book on Indian women in science, 31 Fantastic Adventures in Science by Ashima Freedog and Nandita Jayaraj. And last but not the least, and I'm sure she will continue, she's featured in a science outreach short documentary produced by Will Chilton on the Astro Channel. With this brief, very brief introduction, I ask Jahnavi to take the stage. Thank you.
Hi everybody. Thank you for the introduction. It sounded more glorious than it felt through the way, for sure. About 15 years ago, I was sitting on that side, and I was a nervous wreck trying to make a career. Crazy about geology. Joined geology because I wanted to be a paleontologist, and that was because I watched Jurassic Park in 4th standard, the oldest story ever. But the reason why that was so important was because I wasn't allowed to watch movies. We never went to theatre, so that was the only movie that was an exception, and we actually went to the theatre and watched it. So it became a big deal for me. Coincidentally, I don't know, it sounds a little unscientific to say that sometimes the paths are chosen for you. It's weird, but while clearing up, we've moved a lot of times in the last couple of years, and when I was cleaning up my my book collection and old journals, I still had all my journals from Xavier's, and I found an assignment that I had done in BSc. I don't know if there was some sort of written assignment, like a term paper, and that was about the KT boundary. On something like this. I knew I wanted paleontology, but I didn't know that that was always on my mind. So that and a term paper from MSc IIT Bombay was also on mass extinctions, focusing on Cretaceous Paleogene boundary. And then when I applied for PhD positions, I did not apply to many schools because application process for PhD is quite expensive. Each application costs a couple of $100, and you have to be really sure where you're applying and make sure you will actually get in. So I just applied to like 7 or 8 places, and the only place that I got accepted was Princeton. Cretaceous Paleogene boundary. So I don't know what's the deal with me and this particular event, but it's somehow extinctions and let's put it this way. Extinctions and faunal turnovers tell us about the thresholds of life on this planet, the brinks to which life has gone, almost died, but survived. So that, I think, is something that makes research on mass extinctions and faunal turnovers so interesting. In addition to that, I get a lot of questions on why micropaleontology, why paleontology. So the thing is, I also do a lot of geochemistry and other sorts of things. It's not just forams or describing. The kind of paleontology we are introduced to, which is necessary at the bachelor's level, is describing fossils and drawing them. That's not all you do eventually. It changes. What you're doing is something which is classical, in the sense people who were contemporaries of Charles Darwin, everyone must have heard of Darwin, Lyell, Georges Cuvier. So this was a classical era when people were recognizing fossils and their existence, and that they're not freaks of nature but actually organisms that had lived millions of years ago. So when this was going on, the only way they could communicate with each other as scientists was by drawing them, describing them, and trying to classify them as, in the tree of life. So what we do in bachelor's as paleontology, although for some people it might be extremely boring, is we are mimicking these founding fathers of paleontology in some sense, and we are trying to live through that process so that we familiarize ourselves with what do we do when we find a fossil. It's not just about finding and reporting it, it's about what does it mean, what world was it from, how was the planet when it lived, right? So that's the interesting part about paleontology, and I don't think you can isolate research areas anymore. You have to have geochemistry, you have to have sedimentology, you have to have stratigraphy. So it makes it very exciting. So with that, I think let me start with my talk, which initially will be about my experience with science and what I have worked on. Not necessarily just my PhD, but how it has evolved from my perspective, my experience with science. And just feel free to stop me at any point if you think things are not making sense, or it's going too fast or too slow, or because I'm trying to tailor it to BSc SYT by sort of a narrative. So I will not go into too many technical details, it will be more like a story. In case you need more details after the talk, if you need less details, please raise your hand and let me know so that I can accordingly tailor it. Okay, so I'm Jahnavi and I'm currently in the Department of Earth Sciences, IIT Bombay. And I have, science is always collaborative, so I've worked with a lot of people from Princeton, from University of Lausanne, Switzerland, from Portugal and many more. I've not really put their emblems here, but that and to do science, unfortunately, you cannot pay from your own pocket. It gets very expensive, so you need funding. And this is something that nobody tells you or you don't know when you are aspiring to be a scientist, but the only way you can get this money is that you win a lottery, which is less likely, or you write proposals and you get funded. You write a proposal which makes sense, that shows that you have read a lot, that you have a good scientific question in mind, submit it, and then the funding body decides if you are worthy of being given some money. It should not be a waste for them, right? So then they will decide to give you money. So my research is funded by Scott and Tuttle funds from Princeton University, from some NSF grants, which were my advisors, and also DST Inspired Faculty Award, which is basically 5-year funding, couple of lakhs per year, so that you can buy your chemicals, set up your lab, buy microscopes, so that's where the money comes from. So I will start with, again, a little bit more on the mass extinctions part. How many of you are aware of Google Scholar to look for publications? Most of you would. So it's just the search engine where you can look up publications, right? So if you go to Google Scholar and hit mass extinctions and put a filter, published papers year filter, and you put, let's say 1980 to 1990, just because. So if you put 1980 to 1990, you see about 3 papers, 3 listings, not really a lot. And then if you change that to, let's say 1990 to 2000, you see more than 3, maybe up to 10 publications. I'm not talking about what they are about, just research on mass extinction. That could be something about biodiversity loss going on today, or it could be about the case boundary, it could be about the Permo-Triassic, it could be any of these. You see a couple of papers. But then if you look at 2000 to 2010, you see at least 3 pages full of 10-15 publications in each page, and then it just increases exponentially in the last 10 years. So why do you think this is happening? Why is there such an increase in people researching mass extinctions? We have a major biodiversity crisis going on right now. Humans have pretty much killed everything else on this planet. Everything else that's not directly useful to us, and what's useful to us we believe, right? That's what is going on, and we don't feel it on a daily basis, but we have single-handedly brought the situation comparable to the last big 5 mass extinctions that the Earth has witnessed in the last 540 million years, Paleozoic. How would you ask? This is a figure from a paper, but let me make it easy and walk you through it. I don't think you can see the pointer, so let me use this. Yeah, so this is, you will see a lot of these very complicated, apparently complicated plots on publications. The x-axis is extinction magnitude. This is what percent of species have gone extinct, right? If there were 100 species, out of 100, how many went extinct in a certain event or an interval? So that's x-axis. And for something to qualify as a mass extinction, you need to have more than 70-75 species out of 100 going extinct, right? 75% or more species going extinct is qualified to be called a mass extinction. If it's less than that, it's not a mass extinction. And then there is also something called background extinctions, which are going on all the time, right? So that's your x-axis. And the y-axis is something called E by MSY, which is extinctions per million species years. You may or may not have done this, but you can compute the rates of extinction. How many species going extinct in how many million years, right? So if a lot of species are going extinct in a very short number of years, that's a bad one. A lot of species going extinct over a big time interval may not be a very bad event in the end, right? So that's your y-axis. Now if you look at this, the big 5 mass extinctions of Earth history, I don't know if you have read of these or heard of these, but one is in end Ordovician, end Devonian, Permo-Triassic, Triassic-Jurassic, and the KT. These are the 5 that have already happened, right? They plot on this space somewhere. So the green is Permian, and then you have Ordovician, which is a small one here, Triassic, Cretaceous, and Devonian. Okay. So if you just read with this graph, you see that the Permo-Triassic was the worst. It's the highest percent of species loss, and Devonian seems to be the lowest, right? Okay. So now, but then all these extinctions played out on different time scales, right? Some may have played out on a 1 million time scale. That percent of species gone in 1 million years versus the same percentage of species gone in 500,000 years versus the same percent of species gone in 10,000 years means very different things. Same percentage of species disappearing in 25.25 million years is much more catastrophic than something that has happened spread over 1 million years, right? You can sense that. It has to be rapid to be qualified as a bad event, catastrophic event. So if you can normalize these, mathematically you can do that. Bring them back to comparable. You cannot compare apples and oranges. You have to compare apples with apples. This is present day. What extinctions have happened in the past 500 years? Okay. Here, you see the yellow is critically endangered, the white is already extinct, and the red is threatened, which will soon go extinct if we don't conserve them. So if you plot those and you have a trajectory, right? Now, you could have model simulations, let's not go into how it's done, but you can project it. You can project it to find out how long, how much more time do we have for these extinctions to be comparable to a mass extinction. You can do that mathematically. So if you do that, it turns out that we don't have much time left. Best case scenario, it's a couple of hundreds of years. Worst case scenario, it's a couple of thousands of years. So that you feel it better, it could be 2-3 generations of humans. Maybe by the time you have grandchildren, things will be pretty bad already. That's the worst case scenario. Best case scenario, maybe a couple of more generations. But then, at that stage, we will be comparable to the big 5 mass extinctions, and we know what happened in those events. The entire way life, the composition, the biodiversity changed. Most of them went extinct, and only a few very adapted, or maybe just by luck, some species survived. Right? So this is to basically impress upon you that we are very close to a biodiversity crisis, to turn a blind eye or even be skeptical, because you have climate skeptics, kuch ho nahi raha hai. You also have extinction skeptics. We've got hate messages on ResearchGate saying stop scaring people. So it's not scaring people, it's just being aware. And can we risk turning a blind eye is the question. We cannot. We need more people working on what's going on today, also more people working on what has played out, so that we can compare these and understand how long we have left, or can we do something to save and conserve the planet. Okay, so on that note, I think I will suggest some nice books that you can read. These are not heavy technical books, no data thrown at you. This is easy reads. One is The Sixth Extinction by Elizabeth Colbert, very nice book. The Earth After Us, and Ends of the World. They kind of focus on extinctions and the aftermath of extinctions and what might happen, how may we survive. Okay, so quite interesting. Alright, so moving on from this little pep talk on why extinctions are interesting and important to study. Mass extinctions by definition are accelerated extinction rates. You always have extinction species disappearing, but when more species start dying per time, that means something else is in play. There must be an external trigger that's causing extra extinctions. They are associated with ecosystem or geochemical perturbations. They are also defined by loss of more than 70% of existing species, and they are often linked to catastrophic triggers, because if nothing changes, life would also not respond, right? Things would just go on, status quo, business as usual. Usual number of species going extinct and new species evolving. But if you have too many of them that occupy diverse habitats dying together, that means there was some external factor that's affected them, and that's what we call catastrophic triggers. What are these catastrophic triggers? They're usually extraterrestrial impacts, the most adored and celebrated causes. Large igneous province volcanism, that doesn't sound very glamorous, but would have been pretty bad if you know the rates at which volcanism can happen, at the scales at which it can happen. Extreme climate shifts, this can also be a trigger, but it can also be a mechanism. Do you understand the difference between trigger and mechanism? Trigger is something which will start a sequence of events. Mechanism is the steps through which you can cause stress, biological stress. Okay, is this too technical, or are you guys with me? You guys are with me. Okay, good. Also, tectonics can be tectonics and large-scale volcanism can go hand in hand, but be important triggers to changes. Mechanisms, again, climate shifts. You can have warming, cooling. You can have something like ocean acidification. You can have toxicity. You can have anoxia. Have you heard of anoxia? Anoxia. So all these things are mechanisms of stress, which can eventually result in extinctions, right? Okay, so my particular area of research has focused on testing out this hypothesis that there may have been a role played by ocean acidification, which led to the Plantiforam extinctions at the end of the Cretaceous. Okay, so let's get a little bit of background on that. Just a recap on the mass extinctions and which event I will be talking about. You have the end Ordovician, which is a global ice house cooling causing mass extinctions. Then you have the end Devonian, which is basically colonization of land by plants and that causing anoxia in the oceans and causing mass extinctions. Then you have the Permo-Triassic, mother of all mass extinctions, linked to two episodes of extinctions, both linked to large igneous province volcanism. One is Emeshan traps in China and Siberian trap volcanism. Okay. Again, the mechanisms were, the triggers were large igneous province volcanism. The mechanism was greenhouse warming, thermal shock, marine acidification, anoxia, euxenia, if you have heard of euxenia. What is euxenia?
Sulfur-rich water.
Sulfur-rich waters, because oxygen is completely gone, so the next electron acceptor is sulfur available. So that acts as the primary anion in forming, for example, you will have pyrite formation in the water column, right? That. And then we have Triassic Jurassic, which has been linked with the Camp Vol. What is Camp Volcanism? Central Atlantic Magmatic Province. This is when the rifting began and eventually ended up becoming the Atlantic. And then the last one, which is the most recent one for us, back in time, is the end Cretaceous mass extinction, KT boundary mass extinction, which was basically, there is so much interest in it because of the demise of non-avian dinosaurs, and dinosaurs are, you know, popularized by Jurassic Park and the like. So yeah, so this has two triggers, and a lot of debate and controversy follows because you have two triggers so closely spaced in time that we cannot resolve it very well. Is Deccan volcanism in India and Chicxulub impact in the Gulf of Mexico. Okay. Again, the consequences can be quite comparable for both the triggers, but it does include global warming, greenhouse warming, sudden climate shifts, marine toxicity, acidification, and trophic system collapse. Okay, so then to sensitize you so that you feel bad about this event is that these guys are the ones that died out. This is a T-Rex. This is, I think, a plesiosaur, ichthyosaur, mosasaur, pterodactyl, right? Pterosaurs. So these are basically what died out, which was popularized, and this is why we feel so much about the KT boundary mass extinction. But then in less famous extinctions are also about ammonites. They don't go extinct at the boundary, but they start dwindling much before the KT boundary. And then we also have important mass extinctions in the micro fossils. These are plantic foraminifera, and there is coccolithophore here, calcareous. And they seem to have a major crisis towards the end of the Cretaceous. The fact that calcareous organisms are going extinct means that there is some stressor which is, you know, affecting all these guys, a common stressor, and the most obvious that comes to your mind is an acidification event, right? Although we didn't have a lot of evidence about it, it was speculated, but we didn't have a lot of evidence. Let's see what happens. So then the next thing we have, if the slide changes, which it is not, is this is a summary of all the mass extinction events, faunal crisis events through the Phanerozoic, right? You look at the peaks, these are the big 5 mass extinctions. This is Ashgilian, which is end of Ordovician, Frasnian Flammarian, which is end of Devonian. Then you have Permo-Triassic, Triassic, Jurassic, and the KT. Right? The first panel is all about extinction intensity in terms of percent genera of what? Invertebrates. Okay. Second column is about the dates of impact events throughout the Phanerozoic, based on the craters, based on the dimensions, based on the age. And the third is large igneous province volcanic events. So you could see that we're trying to see if there are correlations between these triggers and these effects, extinctions. And it turns out that most of them actually correlate with large igneous province events, but the KT boundary happens to correlate with an impact as well as a large igneous province volcano, which is what makes it so interesting, which is what makes people fight, which is what makes people get their projects funded forever, because we're not able to resolve this. I don't know when people will come to a consensus. Okay, so that's a picture of the Gulf of Mexico and the Chicxulub impact there. This is the subsurface, how the crater looks, and this is an artist's impression of the crater. This is India. This we don't have to explain too much to you guys because you're well aware. In terms of the magnitude, the aerial coverage of Deccan has been compared to the area of France. And in terms of volume, at least the known onshore volume is more than 1.5 million kilometer cube. That's a lot of basalt, right? Of course, it did not pop out in one day, but it has been pulses or episodes of volcanism. They could be catastrophic enough. We'll see how. Okay, so this is another correlation visit, pretty nice. This is by Vincent Cortio and Paul Rene. X-axis shows you ages of continental flood basalts and oceanic plateaus. Y-axis is ages of mass extinctions. Is this ambiguous? Is there any part that you're not able to follow? If yes, please let me know immediately. I don't want you to zone out. Okay, it's as long as you are with me, it's better for the narrative. Okay, so you have events on the y-axis, event dates on the x-axis, and you see that there is a pretty neat correlation between these volcanic events and these faunal turnover and mass extinction events. Of course, each of these dates have error bars of millions of years as a disclaimer. Okay, so right here we have end Ordovician, Devonian, Permian, Triassic, and this is end Cretaceous correlating with Deccan volcanism. So what do we study? What do I study? What do we specifically study is planktic foraminifera. Okay, so these are Cretaceous planktic foraminifera. You can see different shapes and sizes. We're still talking about a microscopic scale, maybe in the range of 63 to 300 micrometers. That's the range. Okay, different shapes and sizes, and we have these from sediments collected from all over this region, about more than 300 kT boundary sites. Some are outcrop sections, some are deep sea drilled cores, but there are samples available for this transition, end of Cretaceous to earliest Paleogene. And this is a small GIF that I made for you people to appreciate where they live, but I don't think because it's a different laptop, this is not going to work. Anyway, so we have, if you think that the lightest blue is the surface of the ocean, and this is depth in the water column. Okay, so planktics can live all the way from the surface of the ocean, 0 meters, all the way to something called the thermocline, where the temperature drops very quickly as you go below in the water column, and also subthermocline. So they live in this entire packet of water column, and once they die, the shells that they secrete will go deposit at the bottom of the ocean, wherever they lived, right there. The only place where they don't get preserved is deeper than the calcium carbonate compensation depth. But everywhere above that, in the open marine settings, you can have planktics. How many, what kind, depends on where, who lives where. Okay. Alright, so that's what we do. We try to study these and then reconstruct the water column stratification. How did they live? What age were they? Because they also have biostratigraphic value, if you know what biostratigraphy is. Okay, so how do we do this? We collect samples. You cannot do any kind of geology without doing field work. You have to have samples, and for that you need to get samples. And if someone sends you samples, by experience I'm telling you, you really don't know what's going on. If someone ships you samples, they're just packets of sediment sitting in your lab. You don't know the head or tail of it. You don't know what's above, you don't know what's below, you don't know what's younger, what's older. You don't know where it's from. So highly recommended that you do your own field work, so that you know exactly where the samples are coming from. That's one of our pictures pre-COVID. This was central India, somewhere near Indore. We're trying to also look at Cretaceous anoxic events and that time interval. So Cenomanian, Turonian, if you've heard of that. So we had gone there, and these are my students. There's a tape measure here and layers of sediments, and we are trying to collect sediments from this layer because we try to do high resolution biostratigraphy, right? So we need to collect samples, we put them in Ziploc bags, label them from what level they are coming from with respect to a datum. So we need to know where, we need to know in what order, we need to know where exactly the sample was collected and what is our annotation or sample number to it, right? And we need to know the geologic and tectonic stratigraphic evolution of that particular basin as well. We need to know all this before you can start working. Bring it back to the lab, or alternatively you can order also deep sea cores from core repositories. Okay, many people like to do that because the preservation from deep sea cores is much better. The forams are much better preserved. That's also a way of doing it. Each has its own pros and cons. We can discuss this later after the talk if you are interested. But nonetheless, once we have the samples in the lab, we break them down to smaller fragments to increase the surface area, if you may, and then put them in beakers and soak them in hydrogen peroxide 3%. There is no great chemistry here. It's just that peroxide will oxidize the organic carbon. Organic carbon plus peroxide equals to CO2, bubbles, goes out. What we are left with is just the sediment residue, no organic carbon. Why do we not want organic carbon? Because once we wash this slurry, we want sediment that can be, that's easy to, it pours out easy, doesn't clump into groups. How can you do quantitative analysis if half your forams are stuck in a lump, right? You need it to be a clean residue. So that's that step. And then we wash it through sieves, okay? And once it's washed through sieves, we get different size fractions of residues, and then we archive them in bottles that you see here, labeled bottles. These labels they have to be authentic to what level in the stratigraphic column you had collected the sample from, because we will plot them later, right? So you cannot afford to make mistakes there when you're doing biostratigraphy. And then equipment wise, I think it's really low maintenance. We just use stereo zoom microscopes, very simple. And then what we do is, let me see if I can escape from the slideshow mode and still have, I hope this is not a disaster. Okay, I don't know if the video will work. I really want it to. Oh, it works. I don't know why it wasn't working. Yeah, I'm just waiting for it to come to a point where I can start explaining again. Okay, so that's the stratigraphic column. Those are the points where we had collected the samples from. This is how we plot what we find. Okay, so yeah, so this is what we collected and then washed, put it on a tray, use a brush, pick the forams, put them on slides like this, and then we try to identify different species, and then basically time lapse of community structure change is what we find. This is how we plot it. Okay, then let me go to the next slide. Does it work? I hope it does. Okay, so once we have the samples ready, let me introduce the KT boundary section to you. We don't have yeah. So just to orient you in terms of how a KT boundary section would look anywhere in the world, a very general sort of framework. Most of the Cretaceous sediments are rich in calcium carbonate coming from the Cretaceous planktic forams. Okay, a lot of calcium carbonate, marley, it could be limestones, could be marls, depends where they were deposited. But they have a lot of forams which contribute towards the calcium carbonate content of the sediments. At the KT boundary, which is usually quite abrupt, in the field you see it as one layer which is reddish, iron-rich layer, red clay layer as it's called, and then it's followed by black clay layer. What does black clay mean? There's no carbonate. So none of the guys which you find in these sediments are found in those. It's empty, it's devoid of carbonate shells, right? That's why there's black clay, and then with recovery of the marine carbonate system, you have slowly increasing amounts of calcium carbonate after the KT boundary. This is a typical lithological storyline for a KT boundary section. And then what do? How do you identify the KT boundary? With the mass extinction of the Cretaceous planktic foraminifera. Remember, it's not the iridium anomaly that marks the boundary. Although a lot of literature, paper, documentaries would make it seem so, the extinction is defined by the extinction. The extinction is not defined by an iridium anomaly. Okay? So the primary marker, identifier for the KT boundary is the mass extinction of these guys and the evolution of the post-extinction, the Paleogene foraminifera, which look very different. If you see, you can see the difference, right? I've tried to scale them. The Cretaceous forams are bigger, nicer, a variety of shapes and sizes, but if after the extinction they are much simpler, smaller. Okay? Alright, so another marker for the KT boundary is a negative shift in the delta 13C. How many of you have heard of delta 13C? What is, you're looking at each other and raising your hand. What is delta 13C? And what affects it? It's primarily a productivity marker, primary productivity marker, because that's the process that really affects it. More primary production, more of lighter carbon goes into the organic matter. That means the water around is more depleted in lighter carbon, and that's the water the forams precipitate their shells from, so they will have a more negative impact, right? So just refresh yourselves in case you're confused. So at the KT boundary, you see a negative 2 per mil shift in the delta 13C. Okay? Alright. Another marker is the iridium anomaly. This is the most popular one though, best known because of the impact. How do we, what's the story behind the iridium anomaly being the most important marker? It's Walter and Louis Alvarez who found iridium rich sediments at the KT boundary in Gubbio in Italy, which was basically what was the premise for suggesting that a extraterrestrial impact is the reason why this extinction happened. Okay, so primary marker for the KT boundary is the mass extinction of the forams. Secondary markers are the geochemical markers. Okay, alright. So the foraminifera that I'm talking about, the transition is really slow. Okay, so you see these also have an age context. There can be some species which tell you what age the sediments are about. And based on that, we can actually come up with a relative time scale or age framework. Older sediments of a certain biozone. Younger than that, another biozone. Younger than that, another biozone, and so on. So for us, there are no absolute dates. We don't read sediments as how many millions of years old, right? We only read them as older, younger, and what biozone they are from. So that's one of the best things about these guys, is tells you two things, at least two things. One is what age sediments, and the other what was going on, environmentally speaking. So very useful. So for a moment, we talked about the biostratigraphy value. Here is the paleo-environmental value. These are assemblages of Cretaceous forams, and what you actually see is before the end Cretaceous crisis sets in, you see these various shapes and sizes and abundance of forams. But with increasing stress, what do you notice? I'll let you observe it. There is a change. Is it just reduction in size? It's a whole different set of species here. But what is changing definitely is the variety has decreased. So the diversity has decreased. In technical terms, the species richness has decreased. Right? The diversity has decreased, which is a measure of stress. Communities that are healthy have high diversity. Communities that are unhealthy have very low diversity and dominance of a particular kind of species, which is what you see here. Can you see that? Too many bugs of the same kind, right? So that particular guy is actually very important. The triserial planktic foram. It's the only long-term survivor of the mass extinction, and also the ancestor of all the new species that evolved after the extinction. The name of the genus is Guembelitria, but you don't have to bother about that right now. Similarly, after the extinction, you see a similar pattern. Initially, you have very few new evolved species. Eventually, you have more number of species and also larger shells. Also, some short-term survivors of the Cretaceous, but they eventually die off, except for this one guy that I told you about, right? So, have you heard, like, you might have heard this thing about if we have a nuclear holocaust, what species do you think is going to survive? So this is like the cockroach of the planktic world. Okay, this would be analogous to the cockroaches of the planktic world in the end of Cretaceous. Okay, then this is a little bit of my work. We tracked the cockroach of the planktic world in terms of time and space. We have samples from Meghalaya, from Israel, different sections from Egypt and from Texas. And for the same time interval, we tracked the abundance of this particular guy, this particular genus. Okay, and based on the acme events, the events where they become dominant in the assemblage, diversity is low and abundance of this particular species is very high. We think of that as a stress event and then try to time correlate it, and tentatively it correlates with the more accelerated eruptions of Deccan volcanism. That was one of the preliminary important finds during my thesis work, but we have a much better age framework for Deccan volcanism by now, because one of the professors at Princeton worked on uranium-lead dating of zircons from red bole layers. Thankfully, I don't have to explain these things a lot to you because you are already aware of all these, I'm assuming. So red bole layers had zircon. Basalts themselves don't have a lot of zircons and it's very difficult to isolate. But the red bole layers apparently have zircons. How did they come there? We can discuss later. But dating those from various different levels in the Deccan stratigraphic pile gives you a lot of dates. And it turns out that they did get older dates at the bottom and younger dates at the top, which means we are doing fine with the dating. And we have a very nice age framework. You see all those levels are where they, so they made a, what is it called, composite kind of a section. You have, you sample different locations and then eventually put it back in its stratigraphic perspective. So you get an age framework, and once you have those dates, and then here is a time scale bar. If you see 66.4, 3, 2, 1, this is age scale, millions of years scale, right? So you just plot it and the thickness between these levels. Can you do that? You can just plot it, the thickness of basalts that are associated, and then you plot the curve. What it shows you, can you interpret this graph? It looks very complicated but isn't. This is the time scale and this is the thickness of flows and the dates that come from these thicknesses. If you plot it, what do you see here? You see a trend, but I would like you to focus on this part. What does it mean? It means a lot of these points are almost vertical right here. What does that mean in terms of the time scale? They're all very close together in time. That means a lot of volume of basalt came out in a very little time, such that they're all giving you the same date. What does that mean in terms of the fluxes of gases that came with the volcanism? Lot of lava, lot of gases. Big impact, no pun intended, on the ecosystem, right? And it happens to be just before the KT boundary. Make sense? Okay, so that was quite compelling, but then what is, if we can, okay, we can understand that volcanism may have been a major contributor, even a trigger, but how does it affect life? So first is the sulfur dioxide. A lot of gases come out, dust, carbon dioxide, sulfur dioxide, nitrogen oxides, halides, right? But the most important ones which are stressors are sulfur dioxide, which will cause a short-term cooling on a decadal scale, but it has a shorter residence time, which means it will be, with acid rain, it will be washed out of the system in a couple of tens of years, right? But in those tens of years, it's going to cause acidification, increased weathering on land, and also acidification in the surface oceans. And that acidification is a little bit of a stress for marine organisms. The extra weathering that is going on the land is also going to dump a lot of nutrients in the shallow marine settings, and that's going to cause increased primary productivity, a lot of anoxia, dysoxia. That's another stress factor, right? Now on the other hand, you have on a longer time scale carbon dioxide, which is a potent greenhouse gas, operates on a thousands of years time scale, and is going to lead to warming. Now, what temperature the proxies record is a combination of how much cooling, how much warming is going on, balance of it. If you have a lot of sulfur dioxide and carbon dioxide, the cooling of this and the warming of this together is going to result in a certain temperature. And usually when we see warming in the record, it's the effects of carbon dioxide overriding the effects of sulfur dioxide. So it's an interplay of residence times, how long does it take for the climate change to kick in, and basically it's a very complicated, we cannot very easily decode this from the proxy record. We can just say warm tha ya cool tha, relatively. That's what we can tell. Okay, all right. So all in all, both actually contribute to ocean acidification, because it's not just warming. Extra carbon dioxide in the atmosphere equilibrates with the surface ocean, and extra carbon dioxide dissolved in the surface ocean will lead to, again, surface ocean acidification, and if it lasts for a longer time, maybe even deep water acidification. Okay, so then this is a nice image from one of the papers. It summarizes, I don't think you can see very clearly, let me read it out. The first plot is shallow reef builders. The second one is benthic foraminifera, the third is planktic foraminifera, the fourth is calcareous nanofossils, and the fifth one is organic wall dinocysts. So this paper didn't make a big deal about acidification at the end of Cretaceous per se, but if you focus on where is end of Cretaceous, this line, you see that there is a big bottleneck for planktics and calcareous nanoplankton. So we know that there is something going on for the planktons, which means surface ocean. There is a surface ocean crisis and it's affecting calcifiers, right? This is I don't think we are over interpreting that. There is some stress which is common to surface ocean planktons which secrete calcium carbonate. Could be acidification. Okay, so that was a conjecture until Eric Font from University of Lisbon. He is a paleomagnetism expert who works on magnetic susceptibility, geochemistry, mineralogy sort of work. So he basically put forth two discoveries. One is that the interval just before the KT boundary at a section called Bidart in France, the final couple of centimeters before the KT boundary, he found a mineral called accagenite. Accagenite. Have you heard of accagenite? It's named after a mine called Akkagen in Japan, where this mineral was reported, and it forms in the air, in the atmosphere, with the reaction of iron and chloride anions. And the morphology of this particular mineral is such, it's very feathery, and it forms in the air, let's put it that way. The morphology is supportive of the fact that it forms in the atmosphere. And it's very delicate, but he found that mineral preserved in this packet of sediments just before the KT boundary. Okay, so there was a lot of skepticism. Ek do mineral grains mil gaye to kya hua? It has to be reproducible, right? Every section should have this to make a big claim that there was acidified atmosphere at the end of Cretaceous. Okay, so that did not gain a lot of popularity, but it's true that he found it there, and it is a telltale sign of atmospheric halide presence, right? But another thing which is more tangible to measure and replicate in different sections is something called magnetic susceptibility of the sediments. Now, if you remember the previous slide where I was talking about continental acidification, continental dissolution, if you have more acidified rains for prolonged durations, during soil formation, pedogenesis, you can actually dissolve the magnet. So usually magnetite is a resistant mineral, won't dissolve very easily, but that can get altered if you have more acidic rains and accelerated different kind of pedogenic activity, right? So if you alter magnetite, if it doesn't remain as magnetite, what will happen to the overall magnetic signature of the sediment forming from this soil? Will decrease, right? Yes or no? Or did I lose you guys? So a particular soil forming during non-acidified times will have a certain amount of magnetite grains, which will eventually get transported and deposited in the basin, rivers, floods, whatever, right? Now switch to an acidified world where there is a lot of acid rain and a different kind of reaction happening during soil formation, such that there is not enough magnetite left, it's altering to something else. And now scoop out this sediment and deposit in the basin. What happens? That sediment will have less magnetite, which means lesser of a magnetic susceptibility signature. So in the same interval that I'm talking about here before KP, he found low magnetic susceptibility for a geologically significant amount of time. And the explanation was that globally it was so acidified and there was so much atmospheric acidification, so much acid rain and continental chemical weathering that it could affect the magnetic susceptibility in the sediment record. Okay, so at this point it's a hypothesis. You know what a hypothesis is, right? Doesn't become a theory until you test it enough number of times and there is no contradiction to it. So it's a hypothesis. So then we went on to think, okay, if you have an acidification event, it should affect forames. But what's the way to do it? How do we show that? Saying that it would have affected is a very different thing, and actually showing evidence is a very different thing. So then we went on to look at the same section happens to have foraminifera, and we could test it out there. The hypothesis being, I don't know if this will play, let's see. Again, all my, is it playing or not? Yes, it is playing. Okay, interesting. I didn't expect it to. Okay, so this is an animation again, just keep an eye on what's changing there. Typically CO2 plus H2O is HCO3 minus plus H plus. So that H plus is the proton which is causing the pH of the surface ocean, right? Which is in equilibrium with atmospheric CO2. Now increase CO2, the amount of proton will increase. Meanwhile, Ca2 plus CO3 2 minus is what is making the calcium carbonate of these shells. Now if you have more H plus because of more atmospheric CO2, this reaction will happen, which means it's depriving the forames from the CO3 2 minus anion, which means there is a calcification crisis. This is what we call, and that's stress for planktic calcifiers. Non-acidified conditions, you have planktic forames and they live, die, and their shell deposits to the bottom of the ocean without a lot of change, right? It will become part of the sediment column. But during acidified conditions, what can we expect if there is acidification? One is they would be stressed out that they cannot secrete the same kind of shells. The walls will be thinner. Thinner walls means they would break more when they reach the bottom of the ocean. Or they could just dissolve in the water column also if it's acidic enough, right? All in all, what we expect is at the bottom of the ocean, in acidified times, you would expect more breakage of these guys than in non-acidified times. Does that make sense to you? Okay, that's a hypothesis. We projected that there is this possibility. Let's test this. Another thing that can happen is that in adjustment to acidification, their overall average size might decrease. The whole species has an average size. Humans have an average height. Some are short, some are tall, but overall there is an average height. Similarly, for any particular planktic species, there will be an average size. Some will be smaller, some will be bigger, but there will be an average size. You can do statistical analysis and see if the average size has decreased in times of acidification. That's another way of testing it out. So now we know that there are some things we can test out to see if there was acidification. That's what we did. In the first attempt, this is how data looks. Very boring, very dry. Just a lot of ranges of species through time, and the red line is the KT boundary, right? But then we focused on these intervals where we had this already ongoing discussion about, acidification, low magnetic susceptibility. We knew that something is going on and that's where we should expect a change. So then what did we do? We looked at the preservation of forames and it actually looked bad in that interval. But just by saying preservation looks bad is not sufficient. It's not scientific enough to say that. So then we had to quantify it. So what did we do? Look at the assemblage and make 3 categories: the good, the bad and the ugly. The good is basically well preserved forams. Bad is poorly preserved forams that show signs of leaching, sugary textures, which means some dissolution effect on them, but they are overall intact. And then the third group was imperfect forams, which are completely fragmented, right? So based on this, and we had to actually work very hard to develop this proxy, but then we applied it to the stratigraphic column in the same section that Eric Font had shown low magnetic susceptibility. So that's the low magnetic susceptibility part, that's the interval of interest, and this is the final couple of hundreds of thousands of years of the Cretaceous. What do we see? And this was by far the only and the best eureka moment that I felt during my work, is that we saw more abundance of the dissolved looking forms exactly in the same interval where you find the low magnetic susceptibility. So something that started off as a continental dissolution event related to acidified atmospheres is also seen in the oceans, right? So maybe the hypothesis is not so bad after all. There is something going on. But is that sufficient? Can we base such a huge claim on observations from one section? No. So we had to look at it from another section, another KT boundary section, geographically away from this one. So the next section was comes back from Austria. What do you see there? Same event, same pattern, same trend, same preservation. So 2 places which are hundreds of miles, kilometers apart, showing the same thing. What does it mean? At least regional, if not global, right? So then eventual research also revealed that in the same interval we also have high anomalous amount of mercury in the sediments. And mercury is it's fast gaining popularity as a proxy for volcanism. Now the jigsaw puzzle starts fitting really well. Low magnetic susceptibility, continental acidification. High fragmentation index, marine surface acidification. Mercury, volcanism. Right? Only thing is, this happens over years. It's not like what I'm telling you today in 1 hour. This is the story of the last 5 to 10 years. You know, I think I was working on way back in 2013. Yeah, it's 10 years. So evolving a hypothesis and chasing it down until you find all the answers takes time. It takes a lot of patience, but it's worth the highs that you get on discovery. Okay, so then the question is, was it just a surface ocean acidification or was it also bottom water? Natural question to ask, right? Is it just processes at the bottom of the ocean? Are we making a hype out of this? Is this, you know, is this even an acidification event? It could be just everything at the bottom of the ocean got shaken up or got dissolved, right? Post-depositional ho sakta hai. It could be just reworking. How do we delete that aspect? How do we exclude, or rather, how do we deduce this, that it's a surface ocean acidification event and not just some post-depositional artifact, physical or chemical breakage? So we look at forams that live at the bottom of the ocean and see what they are doing. Turns out they're not doing much. It's only the surface guys that are responding so much. So now we have isolated the problem to surface of the ocean. Okay. Also, those are my volcanoes for the mercury peaks. Sorry, I missed it. So now, playing the devil's advocate, we ask a lot of questions, because finding something is good, but you can always contradict that. People can always question you and show you that you can be wrong. So you have to think of all possibilities that can lead to the evidence that you have seen. So could this be just transportation and reworking? We actually tried experimental fragmentation. Collect the same bugs, shake them on a ultrasonicator. Don't break. They don't really break. And then, is this just post-depositional dissolution effects? That's when we checked for the bottom water dwellers, and they don't really show any dissolution effects. So it's not so much. If it's post-depositional, both should be affected, right? What lived at the bottom and what lived at the surface. Another thing that could lend a lot of strength to this hypothesis is if there is a biological response, if there is a community structure change, if there is dwarfing, if there is wall thickness decrease, then we could have more evidence for acidification. That's something that we've recently worked on. And then, was it a surface ocean problem or overall? And I already answered part of that. Next question is how acidic should the waters be to cause this kind of a signal? Right? What do we call? What is acidification? What is the present pH of the oceans? 6. 6 is acidic, even on a pH scale. 8.1. Before Industrial Revolution, it was 8.3. We have already acidified the oceans quite a bit. So if 8.3 to 8.1 is acidification, what I'm trying to tell you is the definition of acidification. We are not going below 7 pH. That's not the laboratory definition of acidic. We're talking about a decrease in pH, and that will stress out the guys that require to precipitate calcium carbonate. Right? So from our point of view, acidification is any process that is going to make it difficult for calcifiers to calcify the shells. Okay? Alright, so then what were the next steps? We started looking for these biological effects, if I may call it biological, more like a community structure response, individual foram response. In terms of average size, remember I told you about dwarfing, of selection of smaller forams that require lesser calcium carbonate, because they won't get affected, right? Only the larger ones that require more calcium carbonate will be more stressed. So is that something that we see? So it turns out that there is dwarfing in the same section. Bottom of the stratigraphic section to top, we see a decrease in the average size of many species. And then this is preliminary data. We have actually better data that we have submitted. It's in review, so I've not put it on the talk. Another thing that we see is in that interval that I was telling you about, which is problematic, we also see a lot of abundance of these triserial plant ticks. I told you, the cockroach analogues, the ones that survive anything. And it turns out that the amount of calcium carbonate that goes into making one of the big forams is equivalent to what would make 300 of the small guys, which explains why they are more in times of stress. Of course, there are other biological reasons that we are not looking at right now. There would be other factors, but just from a calcium carbonate perspective, also it makes sense. An acidic ocean can support more population of the smaller guys than that of the bigger ones. Only from a carbonate budget perspective. We're not looking at the biology at all. We don't know much about it actually. Right? Alright, so there is something called interspecific dwarfing, which means within one species the size decreases, and there's also, interspecific and intra. Intraspecific is within a species the average size decreases. Interspecific is when within a group of species in a community, the ones that require lesser calcium carbonate are selected over the ones which require more. And we see all of those. Okay? So then we refined our scale. Instead of just the good, the bad and the ugly, we made a whole series of scores on preservation. And what we did, which is more interesting, is now we took some of these well-preserved guys and put them in acid in the lab. By what do I mean by acid? I don't mean like lower than 7 pH. We tested this out at 8, 7.5, 7, 6.5. Okay? And just for a short amount of time. And what we see is that the longer we expose to them, the poorer the score, the worse they look, which is predictable, but we had to show it. Just predictable doesn't make the cut. Okay? Second thing that we see is that the lower the pH, the more the damage. Also very intuitive. Another thing that we actually saw was different shapes get affected differently. So this will affect how we see them in the stratigraphic record, right? The ones that are bigger, more robust, dissolve less, or at least they are more robust, resistant to dissolution than the smaller ones. And lastly, which is probably the most important point for me from this experiment was, if you expose them to lower pH and then shake them up, they break. Which is exactly what I told in my hypothesis, right? That untreated shells don't break, no acidification, less breakage, and treated shells break more, which is exactly what we see in the fragmentation index record. So it's experimentally confirming the hypothesis and the geologic record data that we saw. Okay. So far, this is what we have done, and some of my students are now working more on these lines just to refine our understanding of how the shells dissolve and what they look like. Another question is it just the western Tethys that we saw this in? Because both the sections that I told you, one is here and one is here. Is it just this oceanography, or do we see it everywhere else? So I did that for a lot of different sections, and we do see the trend in most places just before the KT. Okay. So we know that it's a surface. We know that it was a surface ocean event. It is highly likely that it was ocean acidification because we have enough support for that. Although we are still trying to look for more evidence. And this could have contributed significantly because it's the calcifier extinction that we're looking at. So it's possible that this was one of the important drivers of the extinction, and that also directly this and the mercury spikes and the time interval directly link it to the biggest episode of volcanism that I showed you. Remember the vertical line on the plot of volcanism? That event. The biggest spike or pulse of volcanism just before the extinction might have driven all these. Exactly in what sequence, at what time, stratigraphic record is just imperfect enough to not let us do that. But we can make a relative chronology, and the more the data, the better is our story. Alright, so this is the most recent picture of what's going on, faunal changes, climate change event, warming and then cooling. This is where the acidification comes into picture, and these are all the spikes in mercury which we directly correlate to pulses or episodes of accelerated Deccan eruptions. Now, where does the impact fit into this whole picture, you may ask? What about the meteorite impact? Because everyone loves the impact, let's admit it. So what is it doing? Some people connect the impact with the KT boundary itself, and some people suggest that it was not the boundary but it happened a long time before the impact. Now the point is that if the impact happened at the KT boundary, then it doesn't explain all the crisis that was going on before it. Right? Makes sense. Just chronology of events. If it is what happened at the KT boundary, it doesn't explain what was leading up to it. And if indeed it happened at the time that other people suggest, which is, hundreds of thousands of years before the boundary, it still doesn't have anything to do with the extinction or the crisis that was leading up to it. So exactly where that falls in this record is something that people are still working on to sort it out, see if it was really here or what did it do. One of the things, if you read the literature, you would know is the effects of impacts don't last for too long. It can be very catastrophic, but it cannot last for so long that it will make a significant record in the stratigraphic record. Our sampling intervals are such that we may not be sampling the changes because of the impact. So that is always a deficiency. Okay, so I think that's pretty much the end of my tryst with science. I would always like to thank all the people who are involved, because it's not one person's game. A lot of proxies, a lot of people. One person cannot develop complete expertise in all the things and the proxies that I talked about. It's a group of people working towards the same problem. And I would like to end with a little bit of gyan for the juniors. I don't know how many of you will actually pursue geology. I don't know how many of you will pursue academia in geology. Doesn't matter. Point number one is that there is a huge observational component to geology. It's an observational science. You need to be very keen in your observations. and you need to document it extremely well, for which you actually need to do fieldwork. There is no geology without fieldwork. It's the fun part also, but I don't know. I mean, there is, especially with COVID, there was a lot of change in the culture. We even had field work which was done online. It makes me laugh, but unfortunately, the situation demanded it. I honestly think that's a lot of nonsense, because if you're a geologist, you need to do field work. Otherwise, you cannot trust where the samples are coming from, and you lose out on a lot of detail that you would get if you were actually collecting the samples on field. There's this, for some reason, there is a word called ground truth. I think it makes a lot of sense when we are discussing geology. Okay, so fieldwork, I think, is critical, but you cannot just restrict it to that either. There is a lot more that you should do with your observations. It's not just about documentation that geology is. If you are actually, you need to make sense out of it. There's also observational lab work that you need to do. Okay, and then another angle, which is something that we are trying, is the experiments can also contribute a lot to what you have observed in the field. Of course, for geology, the data comes from millions of years, and there's no way we can do millions of years in the lab. I mean, PhD is for 5 years. You need results. You cannot wait for millions of years. So there's no way everything that has happened in Earth's history can be replicated in the lab, but some things can, like I showed you, right? Some things can be replicated, some things can be validated in the lab. That's one aspect to it. And then I think there is also a computational aspect that people are fast catching up on. This is some pictures that okay, they started working. So these are some of the, I was telling you, sir, about the 4-dimensional X-ray tomography scans. So these are some of those important forearms. Remember, I was talking about different shapes and sizes of Cretaceous forearms. So you're looking at those from an X-ray tomography point of view, and this actually gives you how much volume of calcite is in each of these, and that we are using to actually compute those proportions. How many of this makes this? How many of these makes this? And then map it back to how they survived and see if it makes sense. And this is all we are talking about microscopic scale. This is probably 200, I can't see the scale bar very well, but this would be something like 250 microns. This would be something like 100, 150 microns big, and this would also be similarly sized to this. Okay, I think on that note, I would thank you for your time, and I hope it was interesting. I'm happy to answer any questions that you might have. Which way do we go? Okay.
Yeah, recently I
Hey, one minute, mic. Is there a mic?
Or you can just be louder, or I can come there.
No, 1 minute. We are
Okay.
recording.
Alright,
There's a.
I see. Oh, I should have been more nervous, I guess.
Okay, no problem.
Yeah. So recently I've noticed that a lot of politicians in the US particularly have been looking into the geological record and seeing the data associated with carbon dioxide levels in those ranges. And they've made points that associated with the extinctions that currently we do not have those levels. So they have been saying essentially it's a climate denial.
Are they geologists?
No, they are not. So it's like in the political discourse they've been.
Are they biologists? That explains.
In the political discourse they've been continuously.
No, fine. I mean, completely. I mean, see, it's a half-baked argument, because
Yes.
if you did have more than 1,000 ppm of carbon dioxide in the atmosphere in the Cretaceous, and life still existed. What life? Lizards? Big lizards. We'll have big lizards, sure. Right now we can keep pumping CO2 in the atmosphere, but we as a species, if you're worried about us as a species, then no. That may not happen. That may not exist. Life on this planet will find a way. Cockroaches, maybe the next era is going to be of cockroaches, who knows?
Yeah, it's like, but the thing is, because the overall political discourse is not as educated on the matter,
That's why we need more geologists and then go into policy, because otherwise these people will be running the world.
Yeah, that's my question. Like, what could be done to like make it so that the political discourse?
It's up to you guys. I mean, if you instead want an IT job or a management job, please go ahead. But then your job will pay your salary, and then we'll all die. So think about, don't be so myopic in your career choices. I'm not saying everybody will end up doing geology. And I'm not saying everyone should find paleontology interesting either. I'm just saying that even if you go into management, policy, keep this in mind. And accordingly, try to work towards saving the planet rather than accelerating it towards the end. Well, the planet will find a way, but our end. That's what I mean. Also, you made a very interesting point. I find that kind of mentality, even with denial about volcanism and climate change as triggers to mass extinctions, simply because having an impact, destroy, and cause a mass extinction is convenient, which just means that now we are very safe. There is nothing that can destroy us until maybe an impact comes, and only then will we really be afraid or worried. It gives us a false sense of comfort that everything is okay. Do you follow Greta Thunberg? That's her name, right? Thunberg, whatever. I think she's doing a wonderful job. I mean, you need people like that who voice this concern. It's more convenient to sit in our houses. And one of the analogies she draws is, if your house is on fire, would you just sit in another room and pretend like there is no fire? That's what we are doing in a figurative sense. So yeah, it's a long shot from KT boundary and dinosaurs to this, but the whole point of studying these events, one person cannot study all these events and all the proxies and be an expert in everything. But what we are doing is contribute our little thing to the bigger pool of information so that people make better decisions. And we know the thresholds of survival on this planet. Right? I've recently started watching this Netflix. I don't know how it came up on the page, but it's called The 100. I don't know how many of you have. It's post-apocalyptic Earth, and people have been living in a space station for a while, and then they're sending prisoners back to Earth just to see if Earth. This is after a nuclear. Yeah. So it's interesting, but I think that's not a fictitious world in a lot of ways. Maybe that would happen, who knows. Maybe not because of nuclear explosions, but because of global warming. You can expect many more wars, politics, survival crisis, and that brings out the best and worst in people. So, what was that movie again? COVID ke samay dekha tha, Contagion. Yeah. People, change when it's a crisis. Where it becomes about survival then. So everything is connected for me. You had a question, sorry.
I just want to ask how did those foraminifera that survive or adapt to the environment of an acidified?
A good question. They didn't adapt. It's the reason why I made an analogy with cockroaches is exactly the same. They're something called generalists. Their life strategy is produce a lot of offspring, and that's it. So at least some of them will survive. They have a shorter lifespan. They reproduce a lot. There will be a lot of offspring. So the next round of selection, at least some of the many offspring will survive to the next generation. For instance, if you compare a cockroach with an elephant, what's the lifespan of an elephant? And what is the reproductive cycle of an elephant? One elephant will produce an offspring maybe 30 years later, 40. Cockroach maybe by tomorrow or next week, right? So now if you have a crisis which lasts for, let's say, 10 years, the elephant may not be able to produce an offspring, or even if it produces the offspring, may not reach adulthood. So the crisis will hit the elephants worse than it hits cockroaches. Similarly, now see in that picture that I showed you, it's a whole community of foraminifera, right? When we are talking about Remember that big black page that I showed you with different shapes and sizes? I think I would be faster if I just do this. Get out of slideshow mode. That. This one. So the ones on the left, no, not that. थोड़ा ज़्यादा हो गया. That maybe. It's not going to the page I want. I don't know why. Are we there yet? Are we there yet? Anyway, you can also look at it here. So the bigger ones, they would be more adapted to their environment. But more adapted for survival does not mean that they will survive. Elephants are best for the habitats that they live in. Where you have a big volcanic event or you increase and cause a climate change. So it's not always about adaptability, it's also just about bad luck. So coming back to your question, these guys, they are generalists. They probably would have had shorter life cycles and lifespans, and they would reproduce a lot, so many offspring per individual. And also their numbers are usually restricted probably because of the abundance of other species. Now if other species don't exist, there's no competition, no predation. So these can reproduce as much as possible because they are reasonably comfortable. Even in the stress conditions, they are okay. It may be stress for them as well, but they don't have anybody else to compete with them. So they can, their population can grow unchecked. And that's the Acme event that I was telling you about. When their abundance increases, they dominate an assemblage. So it's not so much about their adaptability rather than their tolerance. They have a wide range of tolerance to temperature, salinity, toxicity.
So then if we're talking about larger cephalopods, then they would have, like, is it more of this generalist idea or is it?
So this idea is relative. Are you comparing a cephalopod and a foram? Or are you comparing within cephalopods some species? Because you can have R and K kind of strategists even within cephalopods. There might be some cephalopod species which are generalists. There may be some cephalopod species which are specialists. But if you're comparing forams and cephalopods, maybe forams are more general than cephalopods. So it's kind of like a relative scale. Depends on what group of organisms you're comparing. Any other questions? Yeah?
Why and how does this atmospheric acidification lead to low magnetic susceptibility?
Atmospheric acidification. Okay, we are talking about. Good question. If you have atmospheric acidification, what will happen to that acidified atmosphere? If it's because of sulfur dioxide, that is going to react with vapor and form H2SO4. If you have extra CO2, will do the same, and from carbonic acid. Eventually these acids rain, even if it's halides, eventually it will rain down on land. So there is a certain, let's say a certain rate of chemical weathering which is going to be accelerated by acid rain, right? Now it could be just the rate getting accelerated, it could also be the mechanisms changing. More resistant mineral grains might start reacting and form some other mineral. And the magnetic susceptibility is basically controlled by how many of these grains are there, right? They are contributing to the net signature of the sediment. So if in a normal scenario you have a certain amount of precipitation, weathering, erosion, deposition, change the scenario to acidified. Now you will have more acid rain, more weathering, less susceptibility signature, and that deposits on top of it. And then continue that for a long time. That entire packet of sediments is going to have lower susceptibility than what was the norm in that setting before the event began. Does that make sense? Anybody else? Okay. Yes.
I just wanted to know how does mercury become a proxy for volcanoes?
Good question again. So people have observed the volcanic exhaust present day, and also a lot of other events where we know that there was large igneous by temporal correlation. We know that there was volcanism, and mostly by actually measuring the amount of mercury in volcanic exhaust. So it's nascent mercury which gets into the atmosphere, rains down with its own residence time, and then it comes into the biogeochemical cycles. Organic material has a certain tendency to sequester mercury. So phytoplanktons, organic material, is going to sequester a lot of mercury and then collect it and dump it to the bottom of the ocean. It's all part of the mercury cycling. So if you have, there's a certain amount of mercury in the lithosphere, but if you have more volcanism, that will dump in extra mercury into the system, which eventually will make it to the sediments. So in times of volcanism, you'll have more mercury. This is the simple relationship if you establish once and check it a couple of different events. It's still in a developmental stage as a proxy. It has a lot of just like I just told you. It gets sequestered by clay minerals, by pyritization, by organic material. So it might look like an event, but it may not be. Just because you have more primary productivity in organic material, which catches more mercury, there need not be a volcanic event. It's just collecting more mercury and dumping to the sediments. For us, it might look like an event, but it's actually not. So in that case, we normalize it. You divide it by the organic material. Amount of mercury divided by amount of organic material will remove the effects of organic material and give you how much mercury was in the system. And then you compare it. Similarly, you can normalize with clay or pyrite. Just to get rid of the effects of these, other processes affecting the concentration. Okay. Yes? Yes.
My question, you mentioned about the zircons and the red holes. Any idea where they came from?
Yeah, so I may not be the best person to answer that, but so what is your understanding about volcanism, especially in case of Deccan? Slow, quiet, may not be, right? I mean, initially it may be slow.
Yeah.
Slow by slow, I'm relatively speaking, like quiet trickle of lavas, but eventually there would be silicic lavas in a later stage of eruption. Silicic lavas are more viscous. They can plug the vents and build pressure like a pressure cooker, and then there will be some level explosions, not explosive volcanism as we understand it, but some level of, and that can really have ejecta depositing. So that can bring in zircons and deposit on the previous flow, and then you'll have a new flow. This is like a very layperson story. I don't understand it better. I'm not a geochronologist, so yeah.
Another question, you mentioned that even the so-called cockroaches of the world, they also were stressed. So do we also see a size change in them? Like the size
Yes, but it's something difficult to resolve because see these from size we are talking about 63 for us it's sieve size is what decides what size of forams you're looking at. So in typical assemblages we are looking at greater than 63. We've not personally done measurements, but visually I know that there are times when they get bigger or smaller. Not yet correlated with events. But another thing that happens is we also look at the fine fraction sometimes, which is smaller than 63 microns. It's very difficult to look at them, but you can have, let's say, 30 microns to 60 microns size fraction. And you also get these guys in that fraction where no other species are found. Very few other species are found. So they are in a huge size range already. And in sections where you apparently are devoid of forams or only some of these guys, when you look at the fine fraction, they're full of these. So yes, it's just that I have not demonstrated it systematically as a size decrease. It's a lot of, they're very small to work with. Extremely small to even measure. Even small to handle and measure. So getting statistically significant data to show that there is a change, and especially with these intervals, is difficult. But we do have, another complication is that in shallow marine settings of the Cretaceous, they behave differently from deeper marine open marine settings. The numbers will vary, the sizes will vary. So there is a lot of variability that way. Not very easy to quantify, but it's there. Yes.
Last question.
I don't know if this
Hey, we can take this up
Yeah.
again later outside,
Yeah,
but
later
yeah.
on.
Okay, then ma'am.
No, go ahead.
You go ahead.
I don't know whether to ask this question or not. So
There is
on
no
a-
question you should not ask. Go ahead.
On an average scale, so how much amount of calcium carbonate is needed to construct a foram?
We have the numbers. I showed it to you in the last slide. Couple of micrometers cube. It's different for different forams, at least based on. See, you're talking about a foram. I can only tell you about a specimen of a species of Cretaceous. It's here. One of these would. Yeah, I don't remember the exact number, but it's a couple of micrometers cube. It's part of this data in here.
Actually,
Oh, you can't see it, okay.
Data, but computing, are you using any software like that?
No, it's a tomography. It's a machine, X-ray machine that does like a layer by layer scan of the foram,
Okay.
and then based on the brightness of the pixels of the image, it will integrate, and there will be a transformation from the number of pixels to how much calcium carbonate it means. So the machine calibrates it, and then it quantifies how much calcium carbonate. Well, for us, the machine doesn't know it's calcium carbonate. It would do that for a coin if you put it in. See, if you have a density contrast and the shell shines up as a brighter part, as you saw in the pictures, and then there is empty space inside, pixel by pixel, layer by layer, it will integrate how much is there, and then based on the space, on the size of the overall shell, it will calibrate it and give you a volume. We didn't do it, but this is
So
from
it is like remote sensing where
not
when the brightness of the image.
sort of, you could
And it's like-
borrowed concept, but kind of. So it's completely done by the algorithm, the software. If there are errors in that, maybe, but this is the best we can get. Another way that we try to check this is have an ultra micro balance, a balance that can be very sensitive to weights, and then we collect like 100 or 500 of these guys, measure the collective weight, right? And then divide that weight by the number of specimens you measured, because one specimen you can't measure, they're too light. So you have the same species, 500 specimens, measure the weight, divide by 500, you get an average weight per shell, and then the density of calcite. So then you can eventually deduce a volume. So you can do both, but they have their own errors, can't help it. I think we're done. All forces.
On behalf of Department of Geology, St. Xavier's College and Parvati Bai Chowgule College from Goa, we thank you, Dr. Jahnavi Punekar, for giving us such wonderful talk. She has highlighted everything, the importance of fieldwork, how you do your sampling, how you collect your data, and most important, after that, what you do with that data. It's not just being on field collecting your samples. It is about how you interpret the data, how you will take out some fruitful information from that data. That is what you all should take away from this, and how to make it simple so that everybody can understand it. So thank you, Jahnavi, for giving them such a wonderful talk. I would also like to thank management for giving us this opportunity to organize this talk. I thank Mr. Dinesh for giving us assistance for getting this audio visual on time and perfectly. Thank you, Dinesh, and I thank you all for being there. Okay? I request now Dr. Praveen Hendricks to hand over the gift of or a token of gratitude from our side. It won't be
So should I come there?
Yes, please.
Okay, from here, from there. I walk from this side or I walk? Oh, okay, okay.
Thank you all for being here. Tea is organized outside. Please have tea.
Yeah, thank you guys for not sleeping. Not many were, so that was a nice. Some of them were like a bit on the way. Mostly not. I had used to it in my class.
Let's wait here for one photograph.